what's the dimension of a subspace? It is the number of vectors in any basis of a subspace. So let's take a look at R2. So a basis for R2 would be the standard basis. It'd be 1, 0, 0, 1. So this basis has two vectors. So we would say the dimension of R2 is 2. It's two-dimensional, which it is, right? And for R3, the basis would be E1, E2, and E3, right? Just like it was, this was E1 and E2 for R2. So for R3, it'd be E1, E2, and E3. There's three of those. So the dimension of R3 is 3. So you just need to count the number of vectors in any basis, and that'll tell you the dimension. Now, we have special names for the dimension of the column space and the dimension of the null space. So the dimension of the column space of a matrix A is called the rank of A. And the dimension of the null space of a matrix A is called the nullity. So we have a matrix here. It's been row reduced, and it hasn't been reduced all the way, but we can see that I have pivots here, here, and here. And that means if we were to set these, let's say if we augmented with 0, if we set this equal to 0 and solved it, okay, then I would have 3 basic variables and 2 free variables, right? These would be free. And these are, the first, second, and fourth columns are what we'd call pivot columns. So the rank is the number of pivot columns. Of a matrix A. If we wanted to find a basis for the column space, I would find the pivot columns, and I would take those vectors and put them in a set, and I would call those vectors the basis. Now the dimension of the null space, the nullity, which is the dimension of the null space, it's going to be the number of free variables in the system AX equals 0. So how many free variables you have will determine how many basis vectors you'll have in the null space. So in this case, we have 2 free variables. So the nullity in this case is 2. We had 3 pivot columns, so the rank is 3. So if A is m by n, where n is the number of columns, then the rank plus the nullity has to equal n. So every column is either a pivot column or it corresponds to a free variable. So those two things have to add up to the total number of columns. The rank and the nullity is how many pivot columns you have and how many free variables you have. So when you add them together, you get n. So we talked about the invertible matrix theorem, and we said if A is square and it's invertible, then we had this big list of things that we said were equivalent. And I promised you that we would add to this list. And that's what we're going to do now. So if A is n by n and invertible, then we're just going to add to our list of things that we know. The column space of A is equal to Rn. So why is that? So if A has got n columns and we row reduce it and we get the identity matrix, which is what we'd have to do if it's invertible, then we've got a leading one in every row. We've got we've got n Rn vectors. So that means the column space would span the entire Rn space. So if that's true, then that means the rank of A is also equal to n. So if the rank is equal to n, then the nullity would have to be equal to 0, because when you add the rank and the nullity, you have to get n. So that means there's no free variables, right? If there's no free variables, your nullity is 0. The dimension of your null space is 0. So the dimension of the null space is 0. That means the null space of A is just got one vector in it. It's the 0 vector. That's another way of saying only the trivial solution, right? We'll only have the trivial solution, then the null space is just going to be the 0 vector. And if the columns of A span Rn, and those columns are linearly independent, then we could say this: the columns of A are a basis for Rn. So they span Rn. They're linearly independent because when we row reduce them, we get a leading one every column because it row reduces the identity. So we get that the columns of A are a basis for Rn.